My dear students, let me welcome you all to a new edition of physics. In this edition, we'll revise the relation between EMF of a cell, electromotive force of a cell, and terminal voltage, and the relation also between lost voltage and external voltage. Also, we'll be able to learn how to solve some simple problems. So let's get started. Electric current and Ohm's law. First of all, what is meant by electric current? Definition of electric current? Yes, it is flow of electrons in solid conductors. In general, it is flow of electric charges in solid conductors. This was about the definition of electric current. And what about electric current intensity? So talking about electric current intensity, it is denoted by, yes, capital I, and it is determined from the relation I is equal to Q over T. Q stands for the quantity of charge, amount of electricity. T stands for time. So electric current intensity is defined as it is the quantity of electricity that passes through a conductor in 1 second. Once again, current intensity will be equal to the quantity when the time is equal to 1 second. So current intensity is defined as the quantity of a charge, quantity of electricity that passes through a conductor in 1 second. And what about the unit of current intensity? It is ampere. So talking about ampere, what about ampere? Yes, thank you very much. Ampere is equal to, yes, coulomb over second, since I is equal to Q over T, so ampere equals coulomb over second. So now we'll be able to define ampere. Ampere, it is the intensity of the electric current when the rate of flow of electricity is 1 coulomb per second. So ampere is current intensity when the rate of flow of electricity is 1 coulomb per second. Okay. And what about coulomb? Coulomb is equal to the product of ampere and second. Coulomb is the unit of amount of a charge, amount of electricity. So when we try to define coulomb, we have to start with the amount of a charge or amount of electricity. So coulomb, it is the quantity of electricity which passes any point in a circuit in 1 second when a steady current of 1 ampere is flowing. Let me say it again. Coulomb is defined as the quantity of electricity which passes any point in a circuit in 1 second when a steady current of 1 ampere is flowing. Okay. And now talking about potential difference. Potential difference between 2 points. The relation that determines the potential difference between 2 points is V is equal to W over Q. So it is the work required. V is equal to W over Q. W stands for the work. So it is the work required to transfer unity charge. Unity charge means 1 coulomb between these 2 points. So once again, potential difference, it is the work required to transfer, yes, 1 coulomb between 2 points. And what about the SI unit of potential difference? It is volt. Okay, since V is equal to W over Q, V is the potential difference between 2 points. W is the energy or work required. Q is the amount of a charge. Okay, V equals W over Q. So volt equals, yes, joule over coulomb. Now we want to define volt. Volt is a unit. So when trying to define a unit, we have to start with the quantity measured in this unit. So we have to start with the potential difference. So volt is defined as, yes, thank you very much, it is the potential difference between 2 points. What about these 2 points? Okay, when a work of 1 joule is required to transfer 1 coulomb between these 2 points. So once again, the definition of volt, it is the potential difference between 2 points when a work of 1 joule is required to transfer 1 coulomb between these 2 points. And now talking about something very important, it is electromotive force. Electromotive force of a cell, or we can call it V battery, VB, okay, or V sub B. What is the definition of electromotive force? Okay, it is the work required to transfer unit charge through the whole circuit. Once again, it is the work required to transfer unit charge through the whole circuit. What does it mean through the whole circuit? Okay, that's to say through the external circuit as well as the internal circuit. As a matter of fact, there is another definition of, yes, electromotive force of a cell. Yes, electromotive force of a cell is its terminal voltage when no current flows. This is very important, and this is, well, this piece of information is so important in solving some problems. So let me, yes, say it again. Definition. Another definition of electromotive force, it is terminal voltage when no current flows. And what about electric energy, W? And we want the formula that should be used to determine, to calculate the electrical energy. What about W? Yes, V is equal W over Q. Since V is equal to, yes, W over Q, so W is equal to VQ. This is the first equation. And from current intensity, I is equal to Q over T. Okay, so Q is equal to the product of current intensity and time. From equation 1 and 2, by equating both of them, so we can say the electrical energy is equal to VIT, VIT. V is the potential difference. I, current intensity, T is the time. Okay, W is the, yes, energy, and it is measured in joules. V, potential difference in volt, and I in ampere. T, time is measured in second, of course. So electrical energy is determined from the formula VIT. Once again, joule is equal to volt times ampere times second. Electric power, yes, it is defined as rate of conversion of electric energy. So what about electric power? It is electrical energy consumed in 1 second. Okay, so it is energy, electrical energy over time, rate of conversion of electric energy. Power equals, as I said, energy over time. So unit of power is watt, which is equivalent to joule over second. Since power is equal to VIT over T, T will be crossed out. So we can say that unit of power, which is watt, is equal to the product of volt times, yes, ampere. Okay. Also, power is determined from the relation I squared R. Okay, if you remember, it was the current intensity I times potential difference IV. And now second expression is I squared R. Also it could be determined from the relation V squared over R. These are the relations that could be used for determining the power. And now talking about Ohm's law. Okay, what about the statement? First of all, we need to define electric resistance. Resistance is denoted by capital R. The resistance of a material is its opposition to the flow of electric current. It is opposition to the flow of electric current. It is denoted, as I said, by capital R and measured in ohms. Also, you should be able to convert kilo ohm into ohm. It is multiplied by 10 to the power of 3. And what about mega ohm? It is multiplied by 10, yes, to the power of 6. Okay, and now we want to, yes, state the law. What about the statement of Ohm's law? Okay, the current flowing through a conductor is directly proportional to the potential difference across its ends, provided the temperature is constant. Current is directly proportional to the potential difference, okay, at constant temperature. So we can say V over I is equal to, yes, constant, and this constant is the, yes, the resistance. So we can say volt over ampere is equal to ohm. Volt over ampere is equal to ohm. So a statement of Ohm's law. Ohm's law states that the ratio of the potential difference V across the terminals of a conductor to the current intensity I is, yes, to the current intensity flowing through the conductor is a constant called the resistance of the conductor. V over I is a constant. V over I is equal to R. This is the statement of Ohm's law. And now talking about the factors affecting the electric resistance of a conductor. Factors affecting the electric resistance. We've got 4 factors. First of all, it is the length of the wire. As a matter of fact, resistance increases as the length increases. So we've got a direct relation between resistance and length when the other, yes, factors are kept unchanged. The second factor affecting the electrical resistance is the cross-sectional area. Area is denoted by capital A, and we've got an inverse relation between resistance and, yes, area. So R is directly proportional to 1 over A. This is the second equation, and of course this is quite true when the rest of factors are unchanged. Third factor is temperature, and finally kind of material. From the 2 equations, equation 1 and 2, we can say R is proportional to L over A. Proportionality is replaced by equality, so a constant is placed. So we can say R is equal to rho E L over A. Rho E stands for resistivity or specific resistance. So once again, the resistance is determined from the expression rho E L over A. L length of the conductor, A is the cross-sectional area. And what about resistivity? Rho E is a constant at a stated temperature. Okay, this constant is known as I said, resistivity or specific resistance. And now we want to define resistivity of a material at a given temperature, and this is very important. Resistivity of a material at a given temperature. What about resistivity? Okay, since R is equal to rho E L over A, so we can say the resistance will be equal to resistivity when the length of the wire is 1 meter, cross-section area is 1 meter squared. So resistivity is defined as, yes, it is the resistance of a wire of that material. Resistivity of a material is the resistance of a wire of that material. The wire should be 1 meter in length and having a cross-sectional area of 1 meter squared at that temperature, okay? Unit of resistivity, and this is very important, it is ohm meter. Unit of resistivity is ohm meter. And now we've got a question, what's meant by resistivity of copper at a given temperature is 1.69 times 10 to the power of negative 8. What's meant by resistivity of copper at a given temperature is 1.69 times 10 to the power of negative 8 ohm meter. It means the resistance of a copper of wire, the resistance of a copper wire 1 meter in length and 1 meter squared in cross-sectional area at that temperature is 1.69 times 10 to the power of negative 8 ohm. Okay, so talking about resistivity, so we mentioned resistance. Okay, and your attention, the unit is changed into ohm instead of ohm meter. And now talking about conductivity of a material, sigma. What about conductivity? It is the reciprocal of resistivity. Yes, resistivity, 1 over resistivity is equal to conductivity. So unit of conductivity, it is ohm, -1, meter, -1. It is ohm, -1, meter, -1. And by the way, ohm, -1, we can call it Siemens. Okay. And now what about the factors affecting conductivity or resistivity? Okay, your attention, because this is very important. Resistivity of a material depends on 2 things, kind of the material and temperature. So resistivity, talking about the factors affecting resistivity, yes, resistivity depends on kind of material and temperature, only 2 factors. But resistance depends on 4 factors, length, area, material, and temperature. These are the factors affecting, yes, resistance, but resistivity depends on, yes, temperature and material. And now what's meant by conductivity of silver at a given temperature is equal to 6.173 times 10 to the power of 7 ohm, -1, meter, -1. Okay, it's all easy for you. The best thing to do here is to convert it into resistivity. So one of this figure will give resistivity. So resistivity equals 1 over 6.173 times 10 power 7. So it will be 1.62 times 10 power -8 ohm meter. And now, yes, it will be so easy for you to, yes, define resistivity. It is resistance, remember, okay? But on 2 conditions, length should be 1 meter, area 1 meter squared. So we can say the resistance of a wire of silver 1 meter in length and 1 meter squared in cross-sectional area at that temperature is 1.62 times 10 to the power of -8. And your attention, please, the unit is ohm. Okay, since we are talking about resistance. Thank you very much. Okay, now let's solve a problem. A student makes a resistor from a length of wire. Okay, he used a length of a wire to make a certain resistor. He then makes a second resistor using wire of the same material. Same material means same resistivity, but of half the diameter and twice the length. So the second wire, yes, What about the second wire? Has half the diameter of the first, and its length is twice that of the first. Find the ratio of the value of the second resistor to that of the first. Okay. Given in the problem, diameter of the second is, yes, half that of the first. Okay. Length of the second is equal to L1 twice the first. Since R1 over R2 is equal to L1 over L2, we've got direct, yes, proportionality between resistance and length, times D2 squared over D1 squared, so it is half times 1 over 4, it will be 1 over 8. This is the ratio between R1 over R2. And what about the ratio between R2 to R1? Of course, it is 8 to 1. Another type of questions. What happens when a wire of resistance R is reshaped such that its length is doubled? So the wire is melted and reshaped such that its length is doubled. With respect, we want what happens with respect to the new resistance of the wire. What happens to the resistance of the wire? If the wire is reshaped and its length is doubled. Okay. Resistance is, yes, quadrupled. Resistance is quadrupled. The question is why? Okay, when we increase the length, when the length is increased, area is decreased. So length is doubled, area is halved, and each one of them will affect the resistance by doubling the resistance. So it will be quadrupled. Quadrupled means it is made 4 times greater. Okay, so another item, what happens when a wire of resistance R is reshaped such that its area is doubled with respect to the new resistance of the wire? Okay, your attention. Area is doubled. When area increases, resistance decreases. So area doubles, resistance, yes, is halved. And also there is something important. Increasing the area will shorten the length. The length will be halved. Okay, this is another factor, and a resistance will be halved because of the length. So the final result will be, yes, resistance is quartered, is decreased to 1 over 4 its initial value. Okay, this is very important. What happens when a wire of resistance R is reshaped such that its area is halved? With respect to conductivity of the wire. Okay, now let's remind you with something very important. Conductivity as well as resistivity, yes, what about both of them? They depend only on temperature and material. That's to say they are changed when we change material and temperature. We didn't change either of them, so it remains unchanged. Conductivity is unchanged since it depends only on kind of material and temperature. Okay, so conductivity is not changed. And now talking about combination of resistors, how resistors are connected together. As a matter of fact, we've got 2 methods to connect resistors. First of all, it is series connection. Okay, it is in front of you. We've got just one path for the current to flow. One path means one current intensity. V1 is the potential across R1, V2 potential across R2, and V3 is the potential across R3. Total potential required, V total, is the sum of all of them, V1 plus V2 plus V3. So we can say IR total is equal to IR1 plus IR2 plus IR3. And don't never forget, in series connection, we've got the same current intensity, which will be crossed out, so we can say R total is equal to R1 plus R2 plus R3. And now talking about the second method of connecting resistors, it is parallel connection. In parallel connection, the current splits. Okay, I splits into I1, that flows into, yes, that flows through R1, I2 through R2, and I3 through the resistance R3. But still something very important. The sum of I1 and I2 and I3 will give the, yes, the total current entering the parallel connection. So I equals I1 plus I2 plus I3. And there is something very important in parallel connection. The potential difference, yes, is constant. It's the same across each resistor connected in parallel. So V1 is equal to V2, is equal to V3, and it is equal to the potential difference across the, yes, parallel combination. Okay, I, of course, from Ohm's law equals V over R. Substituting, we can say V over R total is equal to V over R1 plus V over R2 plus V over R3. V will be crossed out, so we can say 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Therefore, when a group of resistors are connected in parallel, the reciprocal, the inverse of the equivalent resistance, is equal to the sum of reciprocals of the individual resistances. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.